All right, 21B students, here is the second part of the integration handout video. Again, we're following this integration handout that's talking about kind of what to do depending on what you see. We've worked through the algebra up to complete the square. So we talked about simplifying it to make it just powers of x, or doing a u-sub if the derivative of one part is equal to another part. And we talked about some tricks in the previous video, long division, partial fractions, and completing the square. Now we're going to talk about trig substitution. So here are some examples. So again, you should definitely refer to this handout. I'm not going to write down all the things, but I'll just point out for trig substitution, right? We are looking for seeing something like the square root of a squared minus x squared, or the square root of x squared minus a squared, or the square root of a squared plus x squared, to help us determine which sort of trig substitution we should do. And really, the kind of thing to keep in mind here is we're just trying to make a trig identity happen. So for example, if I see, for example, let's start with this one, the integral of the square root of 1 minus x squared over x squared dx, I'm going to let x equals sine theta. And the reason is because if x equals sine theta, then the 1 minus x squared becomes a trig identity that I know, one of the Pythagorean ones. So I'm going to write down two things. Thing one, I need dx. Dx is going to be cosine theta d theta. I know in the handout they use u. I prefer to use theta because it's the usual angle name. And then I also want to write down the trig identity. Or so you can do this one of two ways. I'm gonna do it this way first. So I'm gonna rewrite this integral as the integral of the square root of 1 minus sine squared theta all over sine squared theta, and then dx is cosine theta d theta. Now in reality, what I really like to do is I like to take the part in the square root here and just write that over here. 1 minus x squared is 1 minus sine squared theta, and I know 1 minus sine squared theta is cosine squared theta. So I'm going to rewrite this as the integral of the square root of 1 minus, or the square root of cosine squared times cosine theta all over sine squared theta d theta. Square root of cosine squared is cosine. We're ignoring the absolute values here because it's an indefinite integral, so we don't really need to pay attention to that. So we're just going to get the integral of cosine squared theta over sine squared theta d theta. Sometimes this requires a u sub. Here, I think it's just simplifying this as cosine over sine is cotangent. So we really have the integral of cotangent squared theta d theta. And then we're going to use another trig identity, which is that 1 plus cotangent squared theta is equal to cosecant squared theta. So I know that cotangent squared theta is equal to cosecant squared theta minus 1. That's the integral of cosecant squared theta minus 1 d theta. We integrate and we get the antiderivative of cosecant squared, which is negative cotangent theta minus theta plus a constant. And then we have to go back and we have to fill in actually with this. So I don't just want to say that it would be not incorrect, but not wholly correct to say, well, if x equals sine theta, then inverse sine of x is equal to theta, or if you prefer, the arc sine of x is equal to theta. That's correct, but it's not really as right as it can be, although web work will totally take it to write our answer as negative cotangent of the arc sine of x minus the arc sine of x plus c. What is more correct to do is to either use a trig identity or a triangle. I prefer the triangle. So what I mean by triangle is, instead of using this here, I'm going to write, let's go ahead and write up here since I've got room. I'm going to say, well, if sine of theta equals x, then sine of theta really equals x over 1, which I'm going to think of as the opposite over the hypotenuse. So I'm going to draw a triangle where my angle is theta, and sine of theta is the opposite over the hypotenuse. And I can use the Pythagorean theorem to find this third side here. And I can see the question mark squared plus x squared equals 1 squared. So I'm going to get that the question mark squared is equal to the 1 minus x squared, and the question mark is going to be the square root of 1 minus x squared. Pro tip, the unknown side of the triangle is always going to be the square root radical thing that made you do the trig sub in the first place. Always happens that way. Alternatively, if you prefer, you can use a trig and you say, well, I know that cosine squared theta is equal to 1 minus x squared, so the square root of 1 minus x squared is equal to cosine of theta. And then, but really that's not super helpful because I'm trying to find cotangent of theta. So I could do like cotangent of theta is like cosine over sine, and then say it's going to be root 1 minus x squared over x. That seems annoying. I would much rather just say, well, if I use this triangle, I know tangent is opposite over adjacent. So cotangent is adjacent over opposite. And cotangent of theta is exactly going to be the square root of 1 minus x squared over x, just like I said over here. So the better way to do this is to say that our answer is, well, cotangent of theta, we just said cotangent of theta is adjacent over opposite. So it's going to be negative square root of 1 minus x squared over x. Theta still is the arcsine of x. If you just have a theta, you are forced to use the inverse trig function plus c. So thing to think about here is if you're doing a trig sub, if it's an indefinite integral and you're starting off with x's, you have to end with x's. And really, although it's not incorrect to write negative cotangent of arcsine of x, no one wants to see that. Their expectation is to do this sort of thing. Let's do a couple more. Let's try the next one, which is going to be, what do we got here? Yeah, let's do this one up here. Let's try the integral of the square root of x squared minus 4 over x cubed dx. So I know that when it's a minus sign, it's either sine or secant. It's not tangent because tangent starts with t, which looks like a plus. So here I know it's not sine because I don't want sine squared minus 1. I want 1 minus sine squared. So I know it's got to be the secant. So I'm going to let x equal not just secant of theta, but 2 secant of theta. I need two things. I need the dx. That's going to be the derivative of secant theta is secant theta tangent theta, d theta. And then I also like to write the trig identity. So I know that x squared minus 4x, I'm just trying to replace what's inside the square root here. X squared minus 4 is 2 secant theta squared minus 4, which is 4 secant squared theta minus 4. Factor out the 4. Oops, minus 1. And that's equal to 4 secant squared theta minus 1 is equal to tangent squared theta. So x squared minus 4 equals 4 tangent squared theta. And that's what's going to go inside the radical there. So this integral is going to equal the integral of the square root of 4 tangent squared theta over 2 secant theta quantity cubed times dx, which is 2 secant theta tangent theta. It's a little ugly here. So simplify. We're going to get 2 times 2 divided by 8. So I'm going to see a 2 times 2 over 8. And then I have the square root of tangent square, which is tangent of theta. I have times a secant theta tangent theta over a secant cubed theta. Right, that's everything. Tangent, secant, and then secant cubed, yeah. And then we can cancel, or we can cancel a secant here and a secant here. So we're really left with 4 over 8 is 1/2 integral of tangent squared theta over secant squared theta. And where you go from here really depends. There could be a u sub at this point. I don't think there is, because if u is secant, du is secant tangent, and if u is tangent, du secant squared, but I don't really have that. But I can't see an obvious kind of u sub, and we'll talk more about that when we get to the trig section. If I don't see an obvious u sub, what I'm going to do is try and rewrite it in terms of sines and cosines. So I'm going to write this as 1/2 the integral. Tangent squared is really sine squared theta over cosine squared theta. And secant squared is 1 over cosine squared theta. And then I can flip and multiply, the cosines cancel out, and I'm left with 1/2 the integral of sine squared theta d theta. Again, this will come up later when we talk about the trig stuff, but if you're integrating sines and cosines that are all to even powers, you have to use the trig identity that's the half angle identity, meaning we're going to use the fact that sine squared theta is equal to something, 1 minus cosine of 2 theta all divided by 2. And similarly, cosine squared theta is equal to 1 plus cosine of 2 theta all divided by 2. I would factor out the 1/2. So I've got 1/4 integral of 1 minus cosine of 2 theta d theta. Here we're going to have one of those mini u substitutions where I'm going to get 1/4. The integral of 1 is just theta, and the integral of cosine of 2 times theta is going to be sine of 2 times theta divided by 2. I don't know why I put brackets around that. And then we need to do the triangle thing. So the problem here is sine of 2 theta. My triangle isn't going to have the angle 2 theta. When I draw my triangle over here, I'm also taking this here. I'm going to rewrite this as secant theta equal to x over 2. Or if you prefer, you might think of this as cosine theta equal to 2 over x, right? Take the reciprocal of both sides. So drawing my triangle, I just like cosine because I know cosine better in my head. Cosine is adjacent over hypotenuse, so that's going to be 2 over x. Or secant is hypotenuse over adjacent. And then the third side here, I know is going to be the square root that's in my thing here. But you can check, right? It's 2 squared plus this squared. Well, 4 plus x squared minus 4 is x squared. And the square root of that is just x. So yeah, this works. That's a Pythagorean identity. You can also use the Pythagorean theorem if you want to find this third unknown side. But I don't have 2 theta. That's a problem. So the thing is, when you have sine of 2 theta, which sometimes happens, especially with this identity comes up fairly often, you have to use the double angle formula for sine. So it's going to equal 1/4 of theta minus sine of 2 theta is equal to 2 sine of theta times cosine of theta. And then I can cancel those 2's. So I'm gonna multiply out the 1/4 and get 1/4 theta minus 1/4 sine of theta cosine of theta plus c. But then looking at my triangle, sine of theta is opposite over hypotenuse. I should say, first of all, theta itself, well, I shouldn't use this thing I've written here. I should just say that theta is equal to the arc secant of x over 2. So I'm going to be getting 1/4 times the arc secant, or if you prefer inverse secant, that's totally fine. I just use the arc function. I like it better. It's the same function, different name. And then, oh, sorry, minus, I should use white out there, but whatever. Minus 1/4 sine of theta is square root of x squared minus 4 over x. And cosine of theta is 2 over x. And I would probably leave it like that, although we could simplify it a tiny bit. I would probably simplify it because I can't help myself. 1/4 arc secant of x over 2 minus, cancel the 2 there, square root of x squared minus 4 over 2x squared plus c. Okay, let's do one more trig substitution. Let's move this out of the way. I got things all over the place here. Oh, come on, stay out of the way. So one more. Let's do the integral of 1 over the square root of 36 plus x squared dx. So seeing a plus means I know I'm using tangent because t looks like a plus. That's really, I like, it's dumb, but that's how I remember it. So I know that my x needs to equal not just tangent of theta, but 6 times tangent of theta, because I need to get the trig identity. So my dx is going to be 6 secant squared theta d theta. And my 36 plus x squared, I always like to just deal with the stuff that's in the root. It just is, I know it's always going to come up. That's going to be 36 plus 6 tangent theta squared. You can obviously show less work. You're right. I'm kind of showing all the stuff. You could totally jump to saying it's 36 plus 36 tangent squared root and factoring out 36 and jumping straight to 36 times 1 plus tangent squared theta. And of course, as we all know, I tan and get sexy. So this is going to turn into 36 times secant squared theta, right? 1 plus tangent squared theta equals secant squared theta, or I tan and sexy. Best trig identity ever. Anyway, so this is going to become the integral of 1 over 36 plus x squared is going to get replaced with 36 secant squared theta. So I've got the square root of 36 secant squared theta. And then my dx is 6 secant squared theta d theta. So let's see what we've got here. This is going to become the integral of 6. Can't bring that out, whatever. 6 secant squared theta over 6 secant theta. Theta, cancel a bunch of stuff. Cancel a 6, cancel a secant. So you're left with the integral of just secant of theta. This is one that you do need to memorize. The integral of secant of theta is the natural log of the absolute value of secant of theta plus tangent of theta. We'll see. And then we need the triangle. So I know that tangent of theta is just going to be x over 6, right? That's already there. So this is going to be x over 6. And let me just show you how you would do this with a trig identity. So this one would lend itself pretty well to a trig identity. So if I know that tangent of theta, so I'm going to do the trig identity first, just to kind of help you out. So tangent theta is definitely equal to x over 6. And then I know that 1 plus tangent squared theta equals secant squared theta. So if I wanted to get secant theta, I could first take the square root of both sides. Again, ignoring the plus or minus absolute value stuff. And then I can replace tangent of theta with x over 6. So I can say that secant of theta is equal to the square root of 1 plus x squared over 6 squared. Or simplifying this as it'll look, secant of theta will actually equal the square root of 36 plus x squared all over 6, not in the square root. I think that's right anyway. Let's look at the triangle to compare. So doing it the triangle way, which is the way up I would like to do it. This is going to become, so let's see my triangle here. Here's theta. I know the tangent is opposite over adjacent. So I get an x here, I get a 6 here, and the third side should be the square root of 36 plus x squared, and it is. So then, of course, tangent of theta is obviously x over 6. And secant of theta, well, I never remember secant. I remember cosine is reciprocal secant. Cosine is 6 over the square root of 36 plus x squared. So secant is the square root of 36 plus x squared over 6, just like I wrote over here. So my final answer is going to be the natural log of the absolute value of secant of theta, which is the square root of 36 plus x squared over 6, plus tangent of theta, which is x over 6 plus c. And I would probably leave it like that, but some people might simplify this. And since you've got a common denominator here, they might write this as either the natural log of absolute value of the square root of 36 plus x squared plus x all over 6. Well, see, they might even break it apart into two natural logs, which seems weird to me, but whatever. They might write this as the natural log of the absolute value of the square root of 36 plus x squared plus x minus the natural log of 6 plus c. They might even eliminate this and just write it as the natural log of this plus a constant, because natural log of 6 is just a constant that gets sucked up by that plus c there. So there's some trig substitutions. Yeah, I like trig substitution. It's pretty fun, but it is what it is. I will say a lot of trig substitution problems also then require doing some u sub afterwards to get the trig stuff to work out, which we'll talk about in the trig section shortly here. Let me go ahead and go on to the next one. So the last section that's algebraic is the algebraic substitution stuff. So this is kind of like where it's really just a fancy way of saying a u sub that's not going to work out perfectly. So looking at what they say over here, algebraic substitution, let u equal the part that's keeping it from being an exponent problem. That's not really super great. When I think about doing this, basically I'm seeing a problem like this, so x over root x minus 1. It's not really great. You've got a root x minus 1 stuck, so I'm trying to let you be the stuff that's kind of stuck, that's in a parentheses in some way. So I would encourage you to look at this problem. I'm going to do a couple other examples. So let's say I've got the integral of, let's do this one first, x squared over square root of x minus 5 dx. Oh, I should label this. So this is part 5 of the tricks, and this is algebraic substitution. I'm going to pause it real quick and use the restroom, and I'll be right back. Pause. Oh, not pause sharing. Pause the recording. Where did I pause it? Yeah, there we go. Okay, so for this problem, I see some stuff inside the square root. You could either try letting u equal x minus 5 or the entire square root. Usually it's better to start off simple. So I'm going to let u equal x minus 5. I see that du is equal to dx. And then, so again, with a u sub, right, you're always trying to make sure the dx changes to du first, and then deal with everything else. So this is going to equal, so my dx is just du, great. My square root of x minus 5 is the square root of u. And my x squared, well, if I solve for x, so x is equal to u plus 5, then my x squared here is u plus 5 squared. And this is going to be pretty straightforward. We're going to multiply at the top. You're going to get u squared plus 10u plus 25, all divided by u to the 1/2. And then divide each thing by u to the 1/2. So we get the integral of u squared divided by u to the 1/2 is u to the 3/2. 10u divided by u to the 1/2 is 10u to the 1/2. And 25 divided by u to the 1/2 is 25u to the negative 1/2. And now it's just the next one problem. And to differentiate, you get u to the 5/2 times 2/5 plus 10 u to the 3/2 times 2/3. And then you're going to get 25u to the 1/2 times 2. And then plug back in what u is equal to. So we're going to get, let's see, 2/5 times x minus 5 to the 5/2 plus 20/3 times x minus 5 to the 3/2 plus 50 times x minus 5 to the 1/2 plus c. Not too terrible. Let's look at a different example. Let's say that we have, and I don't have enough room on this piece of paper, so yeah. So let's try the integral of x squared over the square root of x minus 5 dx. So unlike the last one where you can't just let u be what's inside the square root because that would just be x, we kind of have to let u equal the entire denominator because that's quote unquote what's stuck. If you prefer, you can think of this as x squared times the square root of x minus 5 to the negative first. So you can see, oh yeah, this stuff here, that's the stuff that's stuck inside my denominator or stuck inside something else, inside some parentheses. So if we let u equal the square root of x minus 5, you might try seeing what du is. My du is going to be the derivative of the square root of x is 1 over 2 root x dx, which is not really showing up in here. So if I start finding du and it doesn't really show up, I kind of start going the other way and start solving for x. So here, if I have the square root of x minus 5 equal to u, the square root of x equals u plus 5, x equals u plus 5 squared. Then dx du equals 2 times u plus 5 to the first, and then dx is equal to 2 times u plus 5 du. And then I can just substitute that in for dx. So what I can do is I can rewrite this integral as the integral of, let's see, x, I'm going to write this one. I don't love writing it like this personally. So x squared is going to be, well, back it up, deal with the dx part first. So dx is 2 times u plus 5 du. X squared is, well, x is u plus 5 squared, so x squared is u plus 5 squared. And then root x minus 5 is just u. Kind of gross. So let's see. If we write this out, we get 2 times the integral of u plus 5 to the 4th times u plus 5 over u du. Or multiplying, writing this out, you get 2 times the integral of u plus 5 to the 5th over u du. U plus 5 to the 5th is kind of a pain. The way I would approach this is to use Pascal, but it's not like super terrible to multiply it out, but it's kind of terrible. So I'm going to multiply it out using Pascal's triangle. And I know I need the row that has 5 as the second number. So, right, that's like u plus 5 to the 0, u plus 5, right? These are the coefficients. So my coefficient of u plus 5 to the 4th is going to be 1 times u to the 5th plus 5 times u to the 4th times 5 to the 1st plus 10 times, if I have enough room here, u to the 3rd times 5 squared plus 10 times u to the 2nd times 5 cubed plus 5 times u to the 1st times 5 to the 4th plus 1 times 5 to the 5th. All over u du. Sorry, it's a little bit tight there. Kind of gross. Right, so it's 1 times u to the 5th plus 5 times u to the 4th times 5 to the 1st, right? Essentially, the powers of u get 1 lesser and the powers of 5 get 1 greater. And then you get 10 times u cubed times 5 squared plus 10 times u squared times 5 cubed plus 5 times u to the first times 5 to the fourth plus 1 times 5 to the fifth. And then depending on the numbers, I might just leave them as is. I know what the powers of 5 are pretty easily, so I'm just going to write them out. So I'm going to get 2 times the integral of, and I'm also going to divide by u. So u to the fifth over u is u to the fourth. 5 times 5 is 25. U to the fourth over u is u cubed. 10 times 5 squared is 10 times 25. U cubed over u is u squared. 10 times 5 cubed is 10 times 125, which is 1250. U squared over u is u. 5 times 5 to the fourth is 5 to the fifth. 5 to the fourth is 625. Multiply that by another 5, and you get 3,125. I'm going to get 3,125, and u over u is just no u's. And then finally, 5 to the fifth is another 3,125, but now I'm dividing by u. And now we just use the power rule. So we're going to get 2 times u to the fifth over 5 plus 25 u to the fourth over 4 plus 250 u cubed over 3 plus 1250 u squared over, I can do the next step. 2 plus 3,125 u plus 3,125 natural log of the absolute value of u plus c. Gross. And then finally, plugging back in what u is equal to, right? Because we do have to do that last step. If I distribute, do I want to distribute the 2? Not really. I'm going to get square root of x minus 5. Great. Square root of x minus 5 to the fifth over 5 plus 25 times the square root of x minus 5 to the fourth, 4, plus 250 times the square root of x minus 5 to the third, 3, plus 1250 over 2 is 625, square root of x minus 5 squared, plus 3,125 times the square root of x minus 5, plus 3,125, natural log of the absolute value of the square root of x minus 5. Plus c. Oof, gross. Okay. I think I had one more example, maybe. Yeah, I do have one more example. I think I did a similar example to this next one in class, but whatever, that's fine. So one more example here. The integral of 1 over the square root of x times x plus 9 dx. And this one, it's not super clear where to go. You just start trying stuff. So here I'm going to let u equal the square root of x, because my du is 1 over 2 root x dx. So I can see that 2 times du is equal to 1 over the square root of x dx. And so this dx over root x, I can replace with 2 du. You might not like that, though. Some people really prefer to do this thing where they solve for dx and say dx is equal to 2 root x times du. And then they go and they say, okay, I'm going to write my integral as the integral of 1 over root x times x plus 9. And then my dx is 2 root x du. And then this root x here cancels with that root x there. That's also a fine way of doing it. Or you could have done it, what I would have done, been like, I have 1 over x plus 9 times 1 over root x dx. And I would have just said, oh, this root x, this 1 over root x dx is exactly equal to 2 du. Either way, you're still getting 1 over x plus 9 times 2 du. But then you have to finish changing things to being in terms of u. So just like before, I have some leftover x's. I have to solve for x here and say that u squared is equal to x. This becomes the integral of 1 over u squared plus 9 times 2 du. Or 2 integral of 1 over u squared plus 9 du. This looks a lot like an arctangent thing, right? If it was the integral of 1 over u squared plus 1, we'd have the arctangent of u as the integral. If u squared plus something else squared, instead of being just the arctangent of u, it's going to be 1/3 the arctangent of u over 3 plus c. If you're not sure about this, you can also check it. So just as a quick check, the derivative of, I'm gonna leave the two out there, sure, of 1/3 arc tangent of u over 3 is gonna be, well, the 2 hangs out, the 1/3 also hangs out. The derivative of arc tangent of some stuff is 1 over 1 plus the stuff squared times the derivative of the stuff, and the derivative of u over 3 is 1/3. Okay, so now check this out. This ends up equaling 2 times 1/3 times, well, actually 1/3 times 1/3 is 1 over 3 squared. And then in the denominator here, I have exactly 1 over 1 plus u squared over 3 squared. If I distribute this 3 squared in the denominator to these terms here, I really get 2 times 1 over 3 squared times 1 is 3 squared, and 3 squared times u squared over 3 squared is just u squared. Look, it's exactly what I integrated. 1 over 3 squared plus u squared, or 1 over u squared plus 3 squared. It really is true that when you integrate 1 over u squared plus, instead of 1 something else squared, you get 1 over that times arctangent of u over that. And then finally, my final answer is going to be 2/3 arctangent of the square root of x. Let's see. So those are some examples of algebraic substitution. It's really kind of just like, if you run out of other algebraic things to do and you still haven't gotten there, try doing a u sub, try letting u equal the stuff that's kind of stuck inside the square root or inside the denominator or inside the power, and then figure out what else you have to figure out. Let's see here. So that's the end of that section. We could move on to trig, but I only have like 15 minutes. I don't feel like it's enough time to really get through all the trig. So yeah, I'm going to end it there, and I'm going to leave the trig part and the iteration and the mixture stuff for another video.